second session. So our first talk is going to be exploits as insecure compilation. And we have Jennifer from Galois presenting this talk.
Thank you. This is joint work with some of my coworkers at Galois. And so in this community, in the secure compilation community, we've spent a long time thinking about what makes a compiler secure. And we have some nice definitions and some nice frameworks for thinking about this. But if you talk to somebody not in this community, then I think that you would get and ask them what is a secure compiler, I think that you would get an answer that really thought about, that was really based around exploits. Like, a compiler is secure if it doesn't introduce exploits. And I think that this is a distinction because for programmers, I think exploits are something that are very intuitive. Over time, we've developed these like intuitive ideas of what it means for an exploit to occur, and it has something to do with, well, I didn't expect it to happen when I was programming, in some way. And so, what we wanted to do in this project was to connect the definitions of secure compilation to talking about exploits in compilers that are not necessarily secure. By applying those formal techniques, we're able to start answering questions like, well, how insecure is this compiler? There can be definitely different stages of this. And in particular, how insecure, what kinds of exploits does it introduce for a particular program, or the particular program that I care about? So in the LangSec community, there's this, and in the exploit programming community more generally, there's this informal definition of weird machines as a computational model that is made accessible by hacking, by exploits. And this is, I think this is important because there have been a lot of attempts to formalize this informal idea of weird machines. And they look something like this. We start out with some, usually a state machine model of a specification of your program. And that state machine should preserve certain security properties that you care about. But then on the other hand, we have an implementation that corresponds more to the code that's actually running on your system. And this implementation might admit additional behaviors that are not related to the specification, and those are the exploits. And those are the things that trigger these weird machines. So there's a couple of difficulties with working with these more formal models in practice. In particular, it's really not clear how to relate the states of the state machine, the specification, to the states of the implementation. And what does it mean for a state in the implementation to actually be okay, actually be safe? They call them sane states. What does that mean? And so I think that a more productive way of looking at these two differences is, of course, as a compiler, or as an insecure compiler. So these two fragments, very naturally, we could shift our way of thinking to think of the source, on the one hand, a higher level source language for which you can easily reason about security properties being preserved of a program that you care about. And on the other hand, an implementation in a lower level target language that maybe admits some exploits, especially when we're thinking about linking or combining it with contexts that can interact with the target language program that in ways that couldn't have been done in the source language. So, the goal here is to take these two perspectives, the secure compilation and sort of the weird machines exploit community, and draw connections between them. So that's the overall goal. What does it look like in practice? So let's suppose that we have a source language and a target language and a compiler between them, right? an exploit of this vulnerable source program B, well, what is it? Here's a proposed initial definition. An exploit is a target context, is a context in the target language that is maybe drawn from some class of attacks, potentially corresponding to the power or strength of the attacker, such that the behavior of A linked with the compilation of B cannot be achieved in the source language. So there is no context in the source language that could have achieved that behavior. Okay, so here's a proposed definition. Is it any good? Well, on the one hand, I want to check that this definition actually matches programmers' intuitions about what an exploit is. Because if this is the thing that we have in our heads, then I want that definition to align. So to do this, we're going to take this definition that we came up with, which really can be thought of as a framework, right? We can instantiate different choices of source language, target language, compiler, etc., and examine example programs and example exploits in these languages to see if they align. So for example, we could think about overall classes of return-oriented programming languages. So in that setting, we have a source program, we have a source language that is C, for example. Assembly would be our target language. Now, in order to do a ROP attack, you really need to know the details of the compiler that it makes in layout and things like that. So we need to fix a particular compiler. And the attacker class, for example, might correspond to command line input. So the attacker is able to send input, but not manipulate the state of memory or anything like that. We also, in this framework, need to think about what behaviors are. So in this case, we can think of the behavior of a program as the set of traces that it might allow. Okay. As another example, we can think about the Spectre example that we saw earlier today that Marco talked about. So in that setting, we can think of the source language as being like the non-speculative semantics, and the target language being the speculative semantics. So the compiler there was really not a compiler at all, right? It was just interpret the same program in two different contexts. The attack corresponds to the ways that the context A in the target language can interact with the program. So that might include preparing the cache, invoking your program on specific inputs, querying the cache afterwards. And the behavior that is observable by that, the behavior that's observable by that attacker corresponds to like the timing information and or whether cache hits have occurred or cache hits or misses have occurred. Okay, so we've run through a number of these examples, and at least I've convinced myself that okay, this definition does make a certain sense. I think that it has potential to be correct. But the definition that we came up with, it's actually kind of non-constructive in a sense. By that I mean it's difficult. So if you have a particular attack and you have a component V, a vulnerable component V, then how do you know if your attack has actually done something that couldn't have been in the source language? That includes like a difficult quantification over all source language contexts. So to make this a little bit more tractable to answer on a case-by-case basis, it was really useful to draw on some of the results in secure compilation, specifically results about robust property preservation. This is becoming a more widely studied interpretation of what it means for a compiler to be secure. In this paper from last year, we have already seen this picture of the hierarchy of property preservation classes. But for now, I'm just going to focus on hyperproperty preservation. And so what this says is that the compiler satisfies robust hyperproperty preservation, RHP, if for all source programs hyperparameters v and all hyperproperties h, if h is preserved by all source contexts linked with v in the source language, then it also will be preserved by all target contexts. So these are hyperproperties, right? Because if we think of behaviors as sets of traces, these are sets of traces. In this paper, right, the authors had proved that there are these property-free. You can present a property-free characterization of this same idea of robust hyperproperty preservation, and so a compiler satisfies RHP if and only if this property-free characterization holds. So for all target contexts, there is some source context such that the behaviors line up. And when we look at this formula, this is exactly the same, or I'd say exactly the opposite property as what we took for our definition of exploits, right? So an exploit is a context such that there is no such source context C. So what that means is that we can transfer that connection for secure compilers into talking about exploits. In particular, the context is an exploit, so A is an exploit, if and only if there is some hyperproperty that is preserved in the source language, but violated by the attack. So, I don't know, this result, I mean, kind of seems obvious when you present it like this, but it wasn't obvious to us when we were starting from the exploit perspective. And so I think that, yeah, this change of framing really was valuable for this. So of course, this connection between the property violation, you might say, and this exploit and this collection of exploits can be extended to the entire hierarchy of robust property preservation classes. So there's no need to think specifically about hyperproperties, but in fact, you could imagine identifying different classes of security properties that you're interested in, looking at the property-free characterization of that, which generally are not hard to show that they actually correspond, by the way. And then, considering the exploit class that you get from negating that property. So, you could certainly imagine considering exploits that violate trace properties, or exploits that violate full abstraction, or control flow integrity, etc. So, for example, let's think about the negation of the trace properties, and you get out something like this. A trace exploit is an attack context such that there is some trace in the behavior of the source program, of the target program, that can't be achieved in the source program. Right? And this is subtly different from the one before, but it has some of the same structures. So, with a little bit of thought about the relationship between these different classes, of course, there's a lot more subtlety that you could do depending on what properties you're interested in. But for example, trace properties are all hyperproperty. Trace exploits are all hyperproperty exploits, but not vice versa. So like the Spectre attacks or other side channel attacks might be hyperproperty exploits, but not trace exploits. So this kind of inverts the hierarchy, right? In that it's easier to show that something is a hyperproperty exploit, but the trace exploits are sort of worse. They're more programmable. I want to think about, let's see, another result that we came up with that comes from thinking about the secure compilation world. So in particular, let's say that you have a series of compiler stages, and you're able to identify one particular compilation pass, or optimization, or whatever, where an exploit exists, right? So suppose we have an exploit just between the intermediate language and the target language. Well, if some properties are satisfied, then we can conclude that that attack also is an exploit. And so I think that this composability between different stages of the compiler is really important, so because you need to understand the structure of the compiler in order to analyze the exploitability, you don't want to do that for an entire very complicated compiler. But instead, if you can do it for a small stage, then you can still know that makes a difference for the entire compiler. If that makes sense. This is actually a little bit of a limited result because of these conditions here, we need to know certain facts about how the other parts. So we showed that there was an exploit here between the intermediate and target language, but you also need to know something about the compilers at a higher level. And so I think that there's maybe room for improvement to make this even a stronger theorem, but it doesn't hold indiscriminately. You do need some conditions. So, some takeaways. I think that in some ways, like I said, this is almost an obvious application of secure compilation work. And in fact, we saw the earlier talk about exercising specters was essentially doing exactly this process for that example. But I do think that there's value in explicitly formalizing this strategy, both to communicate with the other practitioners in other areas, and also for potentially developing tools that can be tools or algorithms that can be reused between different applications. Two, I think that there's value in expanding our ideas about what compilers are. So, we can think about these no-op compilers where we simply consider the same programs in different computing environments. You can also our source language contains state machines. Think about state machine specifications. So yes, I propose a more generous view on what a compiler is in this setting. And finally, in the paper, we the definitions that we present are actually a bit more subtle. We use the definitions of trace-related compilers, as we saw presented earlier, but and we also propose that behaviors need not actually be sets of traces, as we usually think of them. So, and I think that by expanding, by taking away those restrictions, we get even more examples. So, yeah, next steps, I think that there's a lot of opportunities to study these counterexamples to secure compilation, that is, different types of exploits, different classes of exploits. This can be useful both when you're trying to, say, design a secure compiler decisions and want to determine how, whether that decision might introduce exploits between those particular stages that you're considering, or whether those exploits are actually powerful, or maybe they're not as powerful and you don't care about them. And then, of course, these techniques can also be used to understand how, if you're given a compiler that is known to be insecure, how can you insert different kinds of mitigations and increase the security in that way. And I think that's all I have, so thank you.
So I guess I have maybe an answer to your question, and then a question. So I think this is super valuable. Like in an undergrad security class, like we go through like 7 mechanisms. By the end, I'm like, well, each one is trying to get us closer to the abstract model that we see. And I think like you have an answer for like, yes. It seems like that's a good framing of like how do you think of all the mechanisms like I don't know, safe stack and shadow stack and all that stuff. The question that I had was the one where you had like 3 layers.
Yes.
So I'm actually, maybe I misunderstood what you were getting at, but to me it seems like if I go from like a safe language, like let's say bus without on safe, to LLVM to x86, LLVM is busted, but at the end I can still have safe generated x86 code that can export. Right, so like, I'm trying to like, how do you think about like an intermediate layer that is actually an unsafe language, but you essentially only compiles a safe substance?
Right. So, I think that maybe the answer to this question is we don't have to, like when we're thinking about the properties that are violated by these exploits, or whether they're preserved or not, that doesn't have to, we don't have to pick properties that are preserved across the entire language. We only have to pick properties that are preserved across contexts linked with the program that we're considering. So in this case, the program that we're considering, it already has the shape of a compiled C program, for example. Now, if there really are contexts in LLVM that could cause unsafe behaviors, then I'm not sure if that is the case, but where they wouldn't be a problem at a lower level. But if that really is the case, then you could consider, both of those stacks together. But of course, that would be a harder analysis. But this is also only one direction. You can also say if there is an exploit in between this layer, and some precondition holds on that compiler, then you can compose that in the other way as well. So maybe that would be the situation that you're thinking of. So both directions, you can establish results for that.
Okay, one last question.
So exactly on this slide, could you elaborate a bit more what kind, or sorry, where in that hierarchy diagram this property holds? Because for trace properties, this certainly does not hold. The trace that witnesses the exploit of the target to the intermediate may be different from the one that witnesses the exploit from the intermediate to the source. So this would not compose.
About the trace relating compilers to understand that. So they might be different traces, but they have, but they're related. Is that what you're trying to get at?
Yeah, there has to be a relation, right?
Yes.
Because in
Right.
these two, you can have completely different traces.
Yes.
So what is the side condition, or what is the definition of exploit for which this theorem actually holds, this compositionality holds?
What is the definition of exploit?
Intersection
So-
issues.
Sorry?
Behaviors is imbectable. Behavior that you have composed.
Yeah. So this property, behaviors are invertible. Thank you. Is something. It says something about the and target behaviors, and it says that it respects some notion of invertibility. So it does get a little bit subtle in that sense. But so that's what like this condition means, and that's kind of the condition that I'm actually wondering if we can get to be a little bit better, because I'm not sure that this actually holds of all of the interesting examples that I would think about.
Okay.
But beyond the condition, I guess what might be confusing Deepak and others is that what you wrote on the right doesn't quite correspond to what you drew. Like, I think when you say that A is an exploit for V, right, you mean that there is an arrow from A to the top, from the bottom to the top, with
Yes.
red, right? It doesn't mean that you have an exploit at the intermediate language for the source. I think what's written is that you have an exploit at the target for the source program.
Thank you.
Right.
That is what I meant. Yeah. So I didn't mean that there was specifically no relation here between the intermediate and source. What I really meant was A to the source. That's just my diagram not expressing that correctly. So I apologize. We can talk about this more later.
Sure, yeah.
Yeah. Well, unfortunately, we've run out of time. For the POPL, let us thank Jennifer again.